Hello everyone, I am Dr. Osman reporting from the University of KwaZulu-Natal, the premier university of African scholarship. So previously we've looked at energy balancing in non-reacting systems and also in reacting systems. And in such cases we looked at systems where the reactions were known, so we knew what the reaction stoichiometry is. However, what if we don't know what the reactions are? What if the reaction systems are too complex or simply unknown? Now, we've addressed this problem in terms of material balancing by making use of atomic or element balances. We now extend this knowledge to energy balancing, with particular focus again to the fossil fuel industry. So we will look at fossil fuel combustion as well as various chemical upgrading, and we will look at how to deal with these energy balance problems even despite having no idea about the actual reactions. So let's get straight to it. Okay, now as seen before in many cases, particularly in the fossil fuel industry, the reaction stoichiometry associated with various fossil fuels is of course unknown because fossil fuels are complex mixtures of hydrocarbons. Now for material balances, this was overcome by performing element balances, or atomic balances, as we can alternatively call them. And we can extend these principles to energy balancing as well. Now note that the heat of formation of any species is by definition the heat of reaction in which the species in question is formed from the elements. Now heat of formation for any species is actually quite difficult to measure. It can't be measured directly. It usually can't be measured directly, although there are a few that can and have been measured. But typically for most species, the heat of reaction is measured and we ultimately back calculate the heat of formation. So typically if we have, for example, a combustion reaction, we measure that heat of that combustion reaction and we back calculate for the heat of formation. So for fossil fuels and other organic compounds, we simply burn our fossil fuels, or we burn our organic compound, we get our heat of combustion, and we find our heat of formation by back calculation. Now, this particular combustion experiment that I've been talking about, so remember we burn our fuel and we ultimately measure the heat. So this measurement is done using by measuring the gross calorific value. So it's the burning is carried out and we measure the gross calorific value or the high heating value. And this is denoted by QV. So QV, typically in BTUs per pound, is the heat released per unit mass of fuel when it is reacted with oxygen to form ash, liquid H2O, and gaseous CO2, SO2, nitrogen, all at 25 degrees and 1 atmosphere. So I'm not going to go into the details about the physics or the actual procedure of our experiment, of our combustion experiment, but for now it's suffice to say that out of our combustion experiment we simply measure our QV. And this is done by measuring temperatures and other factors to of course get our QV. Now our heat of combustion can be obtained. So this is our combustion reaction, and the heat of combustion is given as follows, as a function of our high heating value. and m bar is the average molecular weight of the fuel, and this is obtained by performing an ultimate analysis of that fuel. Okay, we get it in mass fractions first, and we convert using the molar masses of carbon, nitrogen, sulfur, etc. to get the average molecular weight. Okay, now if we assume an ideal mixture of ideal gases, okay, and this is in the case of using natural gas, for example, we have the following. Okay, so for any fossil fuel, we have negative QV times m bar plus delta PV. Okay, and that's pressure and of course volume. Now if we have an ideal mixture of ideal gases, PV can be represented as RT times the summation of sigma S. Okay, now the summation sigma S reflects the change in the number of moles of the gaseous species expressed in terms of the stoichiometric coefficients of the balanced combustion reaction for 1 mole of fuel. Okay, but hold on. Now we are talking about stoichiometric coefficients of a balanced combustion reaction. But we don't know what the combustion reaction is. We don't have the exact combustion reaction. That is why we are looking at energy balancing with unknown stoichiometry. So now what are we going on about? Okay, so we don't have the exact combustion reaction, but we are given the elemental analysis of our fuel. Okay, whether we are looking at coal or oil or natural gas, we can get our elemental analysis, our ultimate analysis. And we can start with an approximate reaction for our fuel in whatever phase it is, whether it's a solid, a liquid, or a gas. Okay, and this equation is given as follows. We have for any fuel containing carbon, hydrogen, oxygen, nitrogen, and sulfur, if we measure our weight fractions from our ultimate analysis, and we have them, then we simply have this fuel in whatever particular phase plus our oxygen with the following stoichiometry, and that will give us CO2, H2O, nitrogen gas, and sulfur dioxide according to the following approximate stoichiometries. Okay, now this is of course not the actual reaction that's occurring, but it's a start. Okay, so we have an approximate reaction that is perhaps representative for many different kinds of fuels, hydrocarbon fuels. Okay, now all of these W's here are of course mass fractions that we obtain from ultimate analysis of our fuel. So now, looking at this equation here for our heat of combustion, and by noting our actual stoichiometry for our fuel, we get the following equation. Okay, so our delta HC naught is equal to negative QV plus RT over 2, and we have our stoichiometric coefficients based on our mass fractions. Okay, and this is for this particular reaction. Okay, so it's been reduced, and it ultimately reduces to the following. Okay, and we can of course write it out in this way as well by simply eliminating these fractions. Okay, so here it is more clearly. For any fuel, we can approximate our heat of combustion if we know our high heating value or our gross calorific value, QV, and we use the approximate reaction, we can get our heat of combustion. And from there, our heat of formation of our fuel is given by the following. Okay, so remember our heat of combustion is equal to the heat of reaction for our combustion reaction. Okay, so remember that we have delta HR, and that's equal to the heat of formation of our products minus the heat of formations of our reactants. So now if I want to know the heat of formation of my reactant fuel, I can simply take it to the other side and I can take my heat of reaction, which in the case of the combustion reaction is the heat of combustion. I take that to this side, and this is how I get the following equation. Okay, now the heat of formation of CO2, H2O and SO2 has been easily measured. And QV, of course, needs to be measured physically to get our heat of combustion. Now, if we cannot measure our gross calorific value or our high heating value, QV, then an alternative approximation will be to use the IGT correlation, a correlation developed by the Institute of Gas Technology. And we can use the following IGT equation as a function of our various mass fractions of our fuel, of our elements in the fuel. Okay, so QV is in BTU per pound, and W indicates mass fraction on a dry basis. Okay, so that's looking at completely dry fuel. If there is moisture in the fuel, we are neglecting that moisture. Okay, a further approximation is also related to our heat capacities of our fuel, and we can actually approximate these heat capacity expressions using Kirov's correlations. Okay, and these are the correlations as shown. So if we consider any fuel, the fixed carbon in the fuel can have a Cp according to the following expression. The ash content in that fuel will have the following specific heat capacity according to temperature. And then we have two groupings. We have primary volatile matter and secondary volatile matter. Okay, so now our fuel, of course, whether we are talking about coal or oil or gas, they have different hydrocarbons. Now we don't really know exactly what hydrocarbons we have. Okay, it's very difficult to distinguish our various hydrocarbons. However, we can group them up into the more volatile hydrocarbons and less volatile hydrocarbons. So now if we burn our fuel, we find that from our emissions we have primary volatile matter, which is the first 10% of volatile matter that leaves the fuel upon once we're operating at high temperatures. Okay, so that primary volatile matter has been grouped up and found to have a Cp as follows. Then we have secondary volatile matter, which is another mixture of lots of various volatile components, and they are all lumped up and have a Cp approximated as follows. Okay, so there are lots of simplifying approximations and correlations which we have come to rely on, and it has been a subject of continuous study to actually provide more and more accurate correlations, especially for the fossil fuel industry, and this includes the coal, natural gas and oil industry. Okay, so we can get reasonably accurate results from these various correlations. Okay, now before we immediately delve into energy balancing for unknown stoichiometries, let's just take a step back and look at our energy balance. Okay, so let's look at our reactor. Okay, so let me just, so this is a single input and single output. And I of course have dq dt and dw dt. Okay, and I'm going to label this stream 1 and stream 2. So this is my reactor. Okay, so now if we have to draw up an energy balance for this, we would have dq dt plus dw dt. And let's say if I have a certain number of species coming in, a certain number of species coming out, I'm going to have to express my enthalpies in terms of enthalpy out minus enthalpy in plus the effect of my reaction. Okay, so let's look at it. We have the summation of all of our species in stream 2. So NS is for species. Each and every species here is species S, multiplied by the enthalpy of each species S at my temperature T2 for temperature at stream 2 minus my enthalpy at some reference temperature T0. Okay, so I'm adding my reference temperature here as T0. Okay, so these are my outputs. Okay, so I'm going to subtract my inputs. Okay, so that's my enthalpy at T1 minus my enthalpy of each species at the reference temperature T0. Okay, so that's my output, my outlet enthalpy minus my inlet enthalpy. Now I need to account for my effect of the reaction. Okay, so and that is given by R times delta HR, and if it's multiple reactions, I would have multiple reaction rates, overall reaction rates with multiple heats of reaction. Okay, now there is another way to express this if we go back to basics. Okay, so remember that for our reacting systems, any species I, so Ni out is equal to Ni in plus our Vi times R, and this is our overall, our stoichiometric coefficient for each reaction. Now this in reality is actually simply our production rate or consumption rate, depending on whether our species is a reactant or a product. Okay, so this VIR is simply equal to Ni out minus Ni in. So we can replace this here by simply looking at, and we are also obviously also looking at our heats of reaction at our reference temperature T0. Okay, so let me just get another color here. Okay, so I can replace this and simply state it in as a production rate, so that will actually just be the summation of the enthalpy of each species at my reference temperature multiplied by my production rate or consumption rate. Okay, depending whether the species is a reactant or a product. Okay, so this here is equivalent to this here. Now in the case of not knowing our reaction stoichiometry, we can actually replace this and go back to basics and work with our enthalpy of our production rates or consumption rates. Okay, and this is what we can aim to do. So let's look at it once more. I'm just going to rewrite this now. Okay, so that's the output minus the input. Plus my enthalpy at my reference temperature of my production or consumption rates of all of my species. Okay, now we can actually re-express this by looking at our definition of our enthalpies of formation. Okay, now recall that our heats of formation are actually the heats of our formation reaction for each species. Okay, so remember that we are formulating our species from individual elements. So our heat of formation for any species is actually equal to the enthalpy of that species. Okay, and this is at T naught. Minus our summation of our reactants, in other words, the elements that make up the species. Okay, and that's from elements going from E is equal to 1 to E elements. Now, instead of writing our enthalpy here of our species at our reference temperature, we can express our enthalpy in terms of our heat of formation. So instead of this term here, we can change the subject of the formula and say that this HS naught is equal to delta HF, heat of formation, plus my summation here. Now just to look at an example, in the case of methane, remember our formation reaction was our carbon plus half of oxygen plus 2 of hydrogen. Sorry, this is for methanol. Okay, giving me CH3OH, and my heat of formation for this reaction is actually equal to the enthalpy of my methanol minus the enthalpy of each of these elements. Okay, so that's what this term here represents, the heats of formation of these elements here. And this here represents the enthalpy of my product, methanol. Okay, now if we're going to re-express our terms, and in this particular case I'm going to now set my reference temperature T naught to actually be equal to the standard state temperature, in other words 25 degrees. Okay, and this is the only way for me to make use of this actual equation here, because my heats of formation are expressed at 25 degrees. Okay, so I'm setting my reference T naught to be 25 degrees. T2 and T1 can of course be anything, but my reference will be 25. Okay, so I have all of the output stream enthalpies and input stream enthalpies expressed in terms of my reference 25 degrees, and I have this reaction term. And now I can replace this HS at T naught with my heats of formation. So let's write it down. Okay, so this is dq dt plus dw dt. Okay, and these are my outputs once again. Now instead of writing this here, I'm going to write the summation of my heat of formation of each species. Multiplied by my production or consumption rate. Okay, now we can open this out. Once again, let's simply focus on this term here. Okay, and I'm going to say that this particular term, I'm going to multiply it and open it out. So let's have at it. Okay, so this term here is equal to minus the NS1 sorry, this is a change here, right? Delta HFS. Okay, so that's my delta there. Okay, and then multiplying it further and simply rearranging, I have the following. Okay, so this is this entire expression opened out and rearranged, and this term here accounts for each element in each of my output and input streams, okay, for my species. And it's interesting to note that this term here actually becomes zero. It disappears because remember, we have our elements are always conserved. Okay, so our elements for our output and our elements in our input will always be the same. So this term here is actually equal to 0. So now we can express this term here in terms of simply these two terms. Okay, now plugging this back into our original expression. Okay, so here is our original energy balance, output minus input plus our production or consumption rates. So instead of this term here, I'm going to simply plug in this term here, these two summations. Okay, and now I am replacing this term here with this term here. Okay, so plus the summation okay, and this is our energy balance. Now if we rearrange, I can also include the summation into this term here and make this all simply one output term, and I can include this summation for my input into my entire input term. Okay, so let's modify that and look at and see how it looks. Okay, and this is my final energy balance. Okay, if I set my dW dt to be 0, this is what I finally end up with. Okay, so my dq dt is equal to my output enthalpies, including my heats of formation, minus my input enthalpies, including my heats of formation. Okay, so this is a way to get around the fact that we don't really know our reaction stoichiometry. So in the case of element balancing or applications such as coal combustion or gas combustion or gasification, where we don't know the reactions, we can now use this alternative energy balance equation. And as you can see, the advantage of this is that there is no stoichiometric term here. We don't really need to know the stoichiometry of any of these input or output species. We don't need to know how they participate in the reaction. Okay, so now this is the balance, and the way we use this is that we can express each output stream as follows. So our output stream can be expressed in terms of its heat of formation of each species. Okay, I'm just writing this in terms of each species here. So it's simply the standard heat of formation plus the enthalpy difference between the output temperature T2 and my reference T0. Okay, and my T0, of course, is equal to 25 degrees. Okay, so there's one trade-off. We need to use our reference temperature at 25, but this enables us to work with an energy balance where we don't really need the stoichiometric coefficients or the stoichiometry of each species. Okay, and my input stream is written in the same way: delta H Fs naught plus Hs of T1 minus Hs of T0. Okay, and this is for each species. So if we want to go back and look at our reactor and we have many different species in each stream, we simply need to add our delta HF0 for each species and our integral from 25 to whatever our stream temperature is. Okay, so now let's look at how we can use this equation to solve an actual energy balance problem. Now let's look at an example. Okay, a steam oxygen gasifier is fed with 10 to the power 6 of pound moles of a devolatilized char at 1700 degrees Fahrenheit, and they have given us the ultimate analysis of this char. Okay, the char is reacted with steam, and that's fed at 1000 degrees Fahrenheit, and as well as oxygen at 400 degrees. Okay, to produce a synthesis gas. So here is our gasifier, and here's our feed char coming in, together with our steam in stream 2 and our oxygen in stream 3. And we get the following syngas, and we have been given our compositions of our syngas on an H2S and NH3 free basis. Okay, so that's an important point. These are the compositions excluding the H2S and NH3. Okay, they've also given us some other information. The nitrogen and sulfur distribution in the products is not precisely known, but it is assumed that the nitrogen and sulfur will be reacted in the same proportion as the carbon. In other words, the carbon to nitrogen ratio and the carbon to sulfur ratios will be the same for the feed char and the spent char. Okay, so in other words, the ratio of carbon to nitrogen in stream 1 is the same as the ratio of carbon to nitrogen in stream 4. Okay, and this is my stream 4 here, the spent char or the ungasified char. Okay, and the same with our carbon to sulfur. Okay, it's the same in stream 1 as it is in stream 4. Okay, and they've given us another subsidiary relation. The steam rate is adjusted so that we have 1.2 moles of water per carbon in the feed. Okay, so in other words, N2 over N1 of carbon is 1.2. Okay, and they're telling us that the reactor or the gasifier will operate adiabatically at 70 bar, and all of the temperatures of our outlets will be the same. Okay, so the temperature of stream 5 and 4 will be the same. And they want us to calculate the oxygen consumption and the reactor outlet temperature. Okay, so they want this oxygen consumption here and the outlet temperature. Okay, so let's evaluate this problem. We don't know the reactions, the gasification reactions, so in order to find our oxygen input, we will need to conduct element balancing. Another thing that we don't know, another thing that is a bit of an issue, is that we are given the composition of the syngas on an H2S and NH3 free basis. Now, one way to get around this is to treat the mass balance such that we have a separate stream 6 coming out, and that will contain only the H2S and NH3. Okay, we know that in reality this is of course not happening. Everything is coming out in stream 5, but for the purpose of our material balance, we can treat these two components separately as if they are coming out in a separate stream, and we would of course get the same results. Now, in order to find our oxygen input, we need to of course perform an element balance, and here is the element balance. Okay, so in terms of our sulfur, if we want to start with our sulfur, we have sulfur in our output here in stream 6. Okay, our fictitious stream 6, 1 mole of sulfur and 1 mole of H2S, and we also have sulfur coming out in the char as well. And we have our inputs. We have sulfur coming in with the feed char. Okay, and that's about it. That's all sulfur there is. So here's the balance. Okay, input is equal to output for all element balances. So here is my input, which is easily calculatable. and here is my output. Okay, now this is a material balance, so I need to use the molar mass of sulfur, elemental sulfur, in order to correct for this. Okay, so there's a bit of a complication between the mass flows and molar flows, since we have been given the flow rate of our char in mass terms. Okay, now in terms of our nitrogen, we have nitrogen also coming out in the spent char as well as in stream 6. So those are our outputs: 1 mole of nitrogen in 1 mole of NH3 and 1 mole of nitrogen for each molar flow rate in stream 4. Okay, and we also have nitrogen, of course, in our feed char. Okay, so here is our balance. We have 1.3% nitrogen in our char, and these are our outputs. We of course don't know the output of nitrogen as yet in the spent char. Carbon is a bit more tedious to work with because we have carbon in CH4, in CO, as well as CO2, and we also have carbon in the spent char, so that's our outputs. And in terms of our inputs, we have carbon in our feed char. Okay, so this is our input, and that is equal to our output, and I'm using the molar mass of 12.01 to correct for my molar flow rate and write this balance only in mass terms. In terms of my hydrogen, I have 4 moles of hydrogen in 1 mole of methane, 2 moles of hydrogen in hydrogen gas, 2 moles of hydrogen in water, 2 in H2S, and 3 in NH3. Okay, so there's no hydrogen in the spent char. And now on this side, I have hydrogen in the feed char. I also have hydrogen here in my steam in H2O, 2 moles of hydrogen in H2O. So here is my hydrogen balance. These are my inputs. Okay, using my molar mass of elemental hydrogen. And these are my outputs, okay, as mentioned. Okay, and we perform the same balance for oxygen as well. Okay, 1 mole of oxygen in CO, 2 moles in CO2, 1 mole in H2O. And in the case of the inputs, we have oxygen coming in as oxygen gas as well as steam. Okay, there's no oxygen in my feed char. So here are my inputs and here are my outputs. And of course the ash balance is as follows. That's quite simple. All of my ash in the feed char ends up in stream 4 in the spent char. Okay, so it's quite simple to write out these element balances. And if we apply our subsidiary relations, we can find our ratios of our nitrogen to carbon in the feed as well as the sulfur to carbon, and that's equal to the ratios in stream 4. Okay, we also know the flow rate of our steam is equal to 1.2 times the flow rate of carbon in the feed char. Okay, now making use of my element balancing as well as the subsidiary relations, I can ultimately obtain all of my flow rates. Okay, and I can obtain these even in molar terms as well. Okay, so that's my flow rate of H2S and NH3 in the flue gas, the flow rate of the entire flue gas, as well as the flow rate of the spent char, well, of the carbon in the spent char and the nitrogen and sulfur in the spent char. Okay, and finally the flow rate of oxygen input. Okay, so this is what I've been wanting or trying to calculate. So that's the first part of the problem solved. Okay, now the second part is of course trying to find the outlet temperature, okay, which is a significantly bigger problem, or it's a lot more difficult to find. but let's make an attempt and see where we go. Okay, one thing to worry about is that we have a feed char with an ultimate analysis, and we also have a spent char, so we can actually find our heating value, our higher heating value. Okay, that's our QV using the IGT correlation. Okay, so that IGT correlation that we've looked at in the beginning, we can use that to obtain QV. Let me just bring the equations back. Okay, so there's the IGT correlation for QV, and we can use that to ultimately obtain our heats of combustion of the feed char as well as the spent char. Okay, so here's the heats of combustion, and finally we can use that information to obtain our heat of formation. Okay, so we use this equation here. So we use our IGT correlation to find the heat of combustion, and then we use the heat of combustion to find the heat of formation of our feed char as well as our spent char. Okay, now there's no other way to find this because we don't really know the actual molecules of our feed char and spent char, and this is why we need to resort to using high heating values. Okay, but now once we have obtained these heats of formation, then our problem becomes reasonably simpler. We can now look at our diagram here. And another issue with the element balancing, or the fact that we don't know our reaction stoichiometry, is that we will need to perform our energy balancing by using our heats of formation, okay, as we've previously mentioned. And here is how we use our heats of formation. Okay, so if I have to look at for the feed char, for example, I have already calculated my heat of formation, and remember that these heats of formation are standard heats of formation. Okay, so these are heats of formation at 25 degrees Celsius, or if we're looking at it in terms of Fahrenheit, that's 77 degrees Fahrenheit. Okay, so here's our enthalpy for stream 1. Stream 1 is the feed char, and that's simply equal to the flow rate of stream 1, the total flow rate, multiplied by the heat of formation, plus the integral from 77 to 1700 of the heat capacity of the char. Okay, and this will give us the enthalpy in BTUs per hour. Okay, the temperature of stream 1 is at 1700, that's why we are going up to 1700. But notice that my reference temperature will always have to be the standard temperature, 25 degrees Celsius or 77 degrees Fahrenheit. Okay, and we can evaluate the same for the spent char. In other words, for stream 4, we can obtain our enthalpy by the following expression. The flow rate of stream 4, this is the heat of formation, and the Cp, and we currently of course do not know what the temperature is. Now we can obtain our heat capacities using Kirov's equations, which we've looked at previously, okay, at the beginning of this lecture. So that's quite simple to evaluate. Since we know our temperatures for our feed, we can immediately calculate our enthalpy H1. However, we can't calculate our enthalpy H4 because we don't know the temperature. Now let's look at our energy balance. Okay, so we're looking at an adiabatic process. Now if we consider our outputs, our energy output must equal to the energy input because we're looking at an adiabatic process. dq dt is equal to 0. So my H5 plus H6 plus H4 will equal to the H1 plus H2 plus H3. Okay, so the enthalpies of the outputs and the inputs must be the same. And this is it expressed here for the energy balance. Okay, now let's look at our other streams. We have, for example, for H2, we have our steam. And remember that now that we are writing out our energy balancing using standard heats of formation, our reference temperature must always be our standard temperature, 77 degrees Fahrenheit. So we can take our enthalpy H2 from 77 to 1000. Okay, in stream 2 there is only water, so we simply need to retrieve the heat of formation of water. So here's the molar flow rate, the enthalpy of formation, and the sensible heat. In terms of stream 3, there is only an oxygen input and the heat of formation of oxygen is 0. So that's my enthalpy there. In terms of stream 6, my fictitious stream 6, we have two components. So we need to look at the mass flow rate of the H2S, the molar flow rates of H2S and NH3. We need to retrieve the heat of formation of H2S and NH3, as well as the heat capacities. Okay, so that's marginally more tedious, but here it is expressed as follows. And the most tedious would be to solve for the rest of my syngas components. Okay, so I need to retrieve the heats of formation of each of these species, and of course the CP coefficients, the heat capacity coefficients, and I need to know the flow rate of each of these species in stream 5. Okay, so it's expressed here very briefly, but this is actually quite a tedious calculation if you open it out. And remember that we don't know what our temperature is, so we will need to express all of these enthalpies and substitute it right back into our energy balance. And once we can do that, then we can solve for our temperature. Okay, so it can be quite a tedious process, but with the use of software, of course, we can actually make things a lot more simpler. Now, if we had to do this manually, here are the heats of formation that are retrieved, and this is what the expression actually reduces to, where we can ultimately solve for our temperature iteratively. And the final result is 1688.2 degrees Fahrenheit. Okay, and that's the problem solved.